Hello everyone. Welcome to week 11's discussion session. Uh, so let's begin today's session. Hope I am audible. If anyone can confirm kindly. Okay, fine. Okay. So the first question is the maximum delay constraint is we have been given a number of uh, delay conditions and we have to find the correct one. So it has not been mentioned here, but it is we are considering here for the case for an flip flop. Okay, flip flop based circuit. So let us quickly look into the circuit first. Okay, fine. Okay, so let it be the circuit. Let D be the D1 be the input, F F1 is the first flip flop, then we have a combinational circuit. Okay, the here the output, let us call it Q1. Here the output of combinational circuit is D2. Then we have flip flop 2, second flip flop. This is the final output Q2 here. Okay, and the clock, by clock. Okay, so now let us draw all the plots. It is my phi clock, first clock, second clock, and so on. Okay, so it is my first clock, second clock, and let us consider it is a positive edge triggered. The flip flops are positive edge triggered. Okay, so this would be my time period TC, correct? And let D1 be the input here. Okay, so this is D1. Now we know the minimum time before which D1 should come before 5 clock has arrived. The rising edge of the 5 clock has arrived is called, what it is called? It is called setup time, right? T setup. Let me write it in capital. This is my setup time. Okay, now what would be the Q1? It would be a little delayed version of T1. So after clock has arrived, so clock has arrived here, so Q1 would be somewhat here. So this one would be my Q1. Okay, so and what is this delay called from clock to Q? It is called clock to Q delay, right? And as we are considering the worst case delay, so here it would be propagation clock to Q delay. So this one would be nothing but T propagation clock to Q, to be precise Q1. Okay, now after Q1, from Q1 to Q2 there is a combinational circuit. So if I draw my D2 here, if I draw the D2 here, use different color, D2 here, D2 would be a delayed version of this Q1, right? And this D2 should be captured in flip-flop 2. So the designing is such that it goes to the negative half of the here, so that my okay, so that it gets captured in the second clock. Fine. So now here it is, the input is Q1, here the output is D2. Only a combinational circuit is present in mid, in between. So what kind of delay it is? It is the worst case delay here is propagation delay. So it would be, this delay would be the propagation delay, correct? And similarly, as this data D2 should be captured here in the rising edge of the second clock, what should be the minimum delay or minimum time before which TPD should be stable before clock? It is nothing but the my setup time. So this one again would be my T setup. Okay, I am considering that the T propagation delay is such that, because T propagation clock to Q delay are like, they are defined for a given in the, for a given library, these things are defined, but this T propagation delay of the combination circuit, we can control it. So I am considering that T propagation delay is such that it is making an end-to-end uh, situation, that is the TPD is so high, it is the maximum value, which, because even maximum delay has been asked here, so it is the maximum value for which my circuit will work without any setup time violation. Okay, so TPD is the largest value possible, maximum value possible. So the rising edge here would be the exact time, exact T setup time before the second clock, rising edge of the second clock arrives. Okay, so from here you can see, it is clearly understandable that this T clock is divided into how many components? This TC is equals to, first this TPCQ 1 to be more precise, then T propagation delay plus the T setup of the T setup for the rising edge of the next rising edge of the clock. Okay, so plus T setup. Okay, so it is the maximum value of the maximum value of this 3. So my TC should be always greater than or equal to this 3 these 3 delay terms. Okay, if it exceeds this, if my TPD is such that it exceeds TC, then it won't be able to capture properly in the second rising edge of the second clock. Okay, so it is the maximum value of TC. Therefore, what would be TPD? TPD would be nothing but greater than TPD would be less than equal to, right? Less than equal to TC minus TPCQ minus T setup. So this is the correct answer. TPD minus TPCQ minus T setup. Clear? Will there be any negative marking in the exam? Bhavna, till now it is not clear, but you guys will get a mail regarding all the rules before the exam. So don't worry about that. Okay. Fine. So we can move to the next question. Question number 2. Okay, so we have been given a system where a sequential circuit is present, a flop is present here, followed by a number of combinational circuit, uh, combinational circuits, and the output is again fed to the input. So it is flop, a sequential circuit, followed by a set of combinational circuits, again followed by a sequential circuit, right? So let us see. It has been asked to find the maximum clock time period so that it does not violate setup time constraints. Okay. Okay, so I can simply use the formulas that I've got in the previous case, correct? So I know. Okay, let me write it down here. T setup time is 62 pico. Hold time is 10. Sorry, hold time is 10 pico. PCQ is, I think PCQ is 90 pico. Contamination is not needed here, but let me write here. Okay. Okay. For adder, propagation delay is 590. For result mux, propagation delay is 60 pico. For bypass mux, TPD is 80 pico. And for late bypass, propagation delay is 70 pico. Okay. So now we know, question number 2, we know TC is greater than equals to TPCQ plus T propagation delay plus T setup. So TC should be greater than equals to TPCQ is how much? It is 90 pico. 90 pico. T setup is how much? Setup time is given as 62 pico. And what is the propagation delay? Propagation delay will be the propagation delay of sum of all the combinational circuits propagational delays. So it would be 590 plus 60 plus 80 plus 70 picosecond. Fine. So how much it would be? 90, 680, 740, 820, 890, 952 picosecond. Therefore, TC minimum will be 952 picoseconds. Clear? Yes, this is the answer. Everyone clear how I am getting this? Any confusion? Okay, if everything is clear, we can move on. Question number 3. So what is question number 3? What is the TPD of the adder block required to meet setup constraint? The clock period is 1000 picosecond. So now clock period is given and I have to find the propagation delay of the adder circuit. Fine. Same, we have gotten simple equation. Just we have to given different constraints of different variables present inside this equation, we have to find the other variable that has been asked, nothing else. Okay, so we know TC would be, what was the formula? Greater than equals to T PCQ plus T setup plus T propagation delay of adder plus T propagation delay of result mux plus T propagation delay of bypass mux plus T propagation delay of late bypass mux. Clear? So fine. So what is TPCQ? TPCQ is 90 picosecond. Setup time is 62 picosecond. Okay, and adder block I have to find. Let me call it TPD only for simplicity of this adder. I have to find it. For result mux, TPD 60 picosecond. Here bypass mux it is 80 picosecond. And late bypass mux is 70 picosecond. And TC is how much? 1000 picosecond. Therefore TPD is less than equals to 1000 minus 90 minus 62 minus 60 minus 80 minus 70. 90, 160, 240, 300, 362. So 738. Sorry, 90, 150, 220, 300, 362. So 638. So anything less than 638 picosecond would give us the result. So what is less than 638 picosecond here? 637 picosecond. So this is the answer. Maruti, this is week 11's assignment, right? We are in week 11. So it is week 11's assignment. It contains sequential circuits and all. Okay, Karthik, you have a doubt from previous week. Okay, we'll be seeing at last. Okay, after let me complete everything, then we'll be taking up previous week's assignments again. Okay, fine. Okay, now question number. If it is clear, that let's move to question number 4. Okay, so some statements have been given to us, and it has been asked to identify which of them are true and which of them are false. Okay, the first statement is, if non-overlap time equals to 0, the combinational system should have a larger TCD than when compared with a positive non-overlap time. Okay, let us look into it. We know, if you remember, what is the expression for T hold? T hold was, T hold is less than T non-overlap. We know T hold is less than T non-overlap plus T clock contamination clock to Q, generally it is 1, plus T contamination delay of 1. Okay, so if I write the equation, rewrite it in terms of T contamination delay, it would be T contamination delay would be greater than T hold minus T non-overlap minus T contamination clock to Q. Fine. Now let us look into all the statements one by one. For the first statement, it is said that if non-overlap time is 0. Okay, so from here, let me write it. From here it is clear that if uh, if this non-overlap time reduces, first let us see increases. If it increases, what will happen to TCD? A negative term is increasing, so TCD would reduce, right? If non-overlap term is increasing, my TCD would reduce. And if the non-overlap term is reducing, simply my TCD would increase. Correct? It would increase. So the first statement would be if non-overlap time is 0, that is non-overlap time has been reduced to 0, the combinational system should have, it is reducing, it is reducing, right? It is reducing, so my contamination delay would increase, right? So the combinational subsystem should have a larger TCT than when compared with positive non-overlap time is true. Correct? As my non-overlap time has reduced to 0, my TCD should increase when compared to a positive non-overlap time was present. Correct? So it is true. Fine. Now the second one is transfer and phase latches generally have one combinational subsystem between each of the phase latches. Okay, let us look here. What does they look like? Generally, they look like this. There will be a latch followed by a combinational circuit, followed by another latch, another combinational circuit, another latch, another combinational circuit, and so on. L3, C3, so on. Here it would be phi 1, it would be phi 2, it would be phi 1 again, and so on. Okay, so it should be phi 3 and so on. So in transparent phase latches, it is true that generally we have one latch, then one combinational circuit, then another latch, then another combinational circuit, and so on. Okay, fine. So second one is also true. Let's look into the third case. If non-overlap time is greater than 0, the combinational subsystem should have larger TCD than when compared with a 0 non-overlap time. Okay, so it has been mentioned that if non-overlap time is greater than 0, that is non-overlap time is increasing, that is this condition, non-overlap time is increasing, then TCD should reduce. But here it is said that instead of reducing, it is getting larger, so the statement is clearly false. Correct? Similarly, the fourth statement is saying if non-overlap time is 0, that is this condition, the combinational subsystem should have a lesser TCD than when compared with a positive non-overlap time. So we can see TCD is increasing. So the statement that it is lesser is false. So the correct answer is true, true, false, false. Clear, everyone? Okay, hope it's clear. Fine, let's move on. Question number 5. Okay, so it has been mentioned that find the minimum clock time period, but here instead of flip-flop, what they have used a pulse latch. Okay, fine. Okay, now here we know for latch we have two expressions for this TC timing constraint, minimum clock timing period. We have two expressions, and it depends whether my T setup is greater than or equals to the pulse width, thickness of the pulse width. So we can see here T setup is equals to 40 picosecond, and this one, and T pulse width is 156 picosecond. Therefore T setup is less than T pulse width. Okay, then if this is the condition, what is the expression for TC? It would be greater than equals to T propagation D to Q plus T propagation T. Okay, so TC would be greater than PDQ is 92 picosecond, and TPD of this one, and this one, which would be equals to 590 pico plus 60 pico plus 80 pico plus 70 picosecond, rather than 590, 650, 730, 800, 892 picosecond. Okay. So therefore minimum clock period would be 892 picosecond. Therefore TC minimum would be 892 picosecond. Correct? Any confusion, anyone? You have to just you have to just check what kind of system it is, latch based or flip flop based or pulsed latch based, and you have to find the condition that it is satisfying, and you have to find the expression, and then just you have to put the values, and you will be getting the any variable that has been asked to identify to compute. You can compute them easily using the expressions. Okay, fine, then let's move to the next question, question number 6. So the next question is, they have asked us to find the minimum delay constraint for a pulse latch system. Okay, so what would the system look like? System would look like something like this. There will be a pulse latch, and there will be a combinational circuit, followed by another pulse latch. Okay. So here the clock would be a pulse clock width. We'll be seeing how it looks like. Input would be D1, it would be Q1, this would be called D2, this would be called Q2. Fine. So let us look into how this 5P, D1, Q1, D2 would look like. So basically my 5P would look something like this. That is, the clock could be high only for a short duration. Okay. This is the thickness of the pulse width. This is my 5P, and I will consider that D1 has arrived sufficiently before this TPW. Fine. So now how would Q1 look like? How would this Q1 look like? Q1 would be this would be my Q1, and what would be this delay called? As we are looking for minimum delay constraint, so we are looking into contamination delay cases, right? So hold time would come into picture, and this delay would be called T contamination clock to Q, or small q, large Q, fine. T contamination clock to Q, right? Okay, and then this Q would go through this combinational circuit. So my D2 would look like, D2 would be something like this, and this would be nothing but pure contamination delay, right? Because we are looking into minimum timing constraint, so it will be TCD. And we have to ensure that, sorry, sorry, so we have to ensure that this TC contamination clock to Q plus T contamination delay should be more than this pulse width plus the minimum time after TPW till which my next output dish2 should not arrive, and this term is called, what it is called, hold time, right? This delay is called T hold, correct? So for minimum delay condition, what would be the condition? So for minimum delay constraint, my T pulse width, this T pulse width plus this T hold should be less than equals to this two term, T contamination clock to Q plus T contamination delay, implies T hold should be less than equals to T contamination delay minus T hold, T pulse PW plus T contamination clock to Q. Clear? So which one satisfies this condition? Less than. This one. T hold is less than equals to T contamination delay minus TPW plus T contamination clock to Q. So this is the correct answer. Clear, everyone? Okay, fine. Then if it is clear, we can move to the next question, question number 7. How much minimum clock time period TC needs to be designed if T skew is 50 picosecond? Fine. Okay. So, how much minimum clock time period TC needs to be designed if T skew is 50 picosecond? I hope it's clear to you. Okay. So from the previous one, we know that from this question, where? Okay, we know TC minus T skew should be greater than equals to T propagation clock to Q plus T propagation delay plus T setup, correct? Okay, so I have to find TC, and T skew is given as 50 picosecond, and TPCQ is given as again 50 picosecond. The propagation delay would be propagation delay of this one plus this one plus this one plus this one, or this one plus this one, whichever is greater. But here it can be seen that flop plus adder plus result mux would be how much? Sorry, adder plus result mux plus bypass mux propagation delay would be 590 plus 60 plus 80, not bypass, 590 plus 60, and mux 2 is, which is 650, and mux 2 is 110. So for propagation delay, the highest one would be considered, that is 650 picosecond would be considered. So this is my path, actual path that I'm interested in. Okay, so it would be, the propagation delay term would be how much? It will be adder plus result mux plus bypass mux. So adder is 590 picosecond, result mux is 60 picosecond, and bypass mux is 80 picosecond, followed by late bypass mux, which is 70 picosecond. Okay, so this two term has been taken care of, and the setup time is given as 65 picosecond. So TC is greater than equals to 50 plus 50, 100, 690, 750, 820, 900, 965, 965 picosecond. Therefore TC minimum would be 965 picosecond. This is the correct answer. Clear, everyone? Okay, I hope it's clear. You can take a moment to look into it. Sorry. So if it's clear, we can move on to the next question. Question number 8. Okay, so the question number 8 is, in question number 7, what is the maximum value that skew can take before hold violation? Fine. Okay, okay, now let us look into it in details. Okay, so let us draw the circuit. So what represent? There was a flop, followed by an adder, followed by result mux, followed by bypass mux, followed by late bypass mux. And the output was fed back to the input. Okay, and there was a mux 2 to feeding the bypass mux. Okay, so first question is what is the maximum value that the skew can take before hold violation? Okay, fine. So we know we know t hold plus t skew should be less than equals to TCCQ plus TCD. Now from where I have got this expression? Using these two conditions. Uh, okay, fine. So what would be my this? What would be the contamination delay? It would depend upon TCD. Let me write the PD and CD values to make the things clear. PD here is 590 pico, contamination delay here is 100 pico. PD here is 60 pico, contamination delay here is 35 pico. PD here is 80 pico, contamination delay here is 55 pico. Propagation delay here is 80 pico, contamination delay here is 45 pico, right? 590, 100, 60, 35, 80, 55, 80, 45 and 100. TPD here is 110 picosecond and TCD here is 95 picosecond. Okay. Now as nothing has been mentioned, though this mux2 is also being timed by another flip-flop here. Okay, it will also be timed by another flop here. So, and if I consider that everything is similar kind of flop was used, then TCCQ has, I have to consider TCCQ also. But as it is not been mentioned for the time being, I will not consider this part. So I can take this TCCQ to be 0, right? Therefore, my T skew that I need to find would be less than equals to 0 plus T contamination delay minus T hold. Now which there are two paths again, right? One path could be this, another path could be this. Now which path is correct? It will depend upon which path is providing the least amount of contamination delay. So basically this plus this would provide me a contamination delay of how much? Path 1 would provide me a contamination delay of T contamination delay of path 1 would be 100 pico plus 35 pico, which is 135 pico. And this path would provide me a contamination delay of only this mux. So the contamination delay of path 2 would be 95 pico. Therefore clearly 95 pico is less than 135 pico second. Therefore TCD2 is less than TCD1. Therefore path 2, that is this path is my this path would be the path of interest. Okay, so my TCD value would come how much should TCD be? Therefore T skew would be nothing but less than equals to TCD would be sum of mux 2 bypass mux and late bypass mux. So mux 2 is 95 pico plus bypass mux is 55 pico, late bypass mux is 45 pico, and minus TCD, and minus T hold. T hold is given as how much? T hold is given as 30 picosecond. 30 picosecond. Therefore T skew is less than equals to 95. 55 is how much? 140, 150, 195, 165 picosecond. Therefore T skew maximum is 165 picosecond. Clear, everyone? How it is coming? So maximum skew that is allowed in our system would be 100, and maximum skew in the clock that would be allowed in our system is 165 picosecond. Okay. Sorry. Okay, fine. Let's move to the next question. Question number 9. So using the same subsystem as question number 7, how much T skew is allowed before hold time failure occurs if mux 2 input comes from a flop using same clock and characteristics? So exactly same as question number 8, only here I cannot consider the TCQ to be 0. Instead I have to consider the TCCQ as the one as the same clock as a flop of same clock and characteristics. So TCCQ would be how much? TCCQ would be this 35 picosecond. This 35 picosecond, right? Therefore T skew would be less than equals to TCCQ plus TCD minus T hold. So TCCQ is how much? 35 picosecond. 35 pico plus TCD minus T hold is how much? 165 picosecond. Right? We have already found it out. So it will be nothing but 200 picosecond. Therefore T skew maximum will be 200 picosecond. This is the correct answer. Though the answer that has been given in the answers that solution we have, 165 has been given as correct if I recall correctly, but no, it would be 200 picosecond, and similar calculations has also been shown by sir in his lectures. So some mistakes might have been happened while preparing the answer key, but the correct answer is 200 picosecond. Okay, clear? Okay, fine. And you can see when because to improve the skewness, like to increase the limit of time skewness time, we can introduce more delays in the best case solution, that is the contamination path. And as TCCQ has been added, so my T skew has improved from 165 picosecond in the previous case to 200 picosecond when TCCQ was considered. Okay, so let's move to the last question of the day. For a transparent latch, it has been asked to find the minimum delay constraint. So the minimum delay constraint for a transparent latch is, I have been given multiple equations. I have to find the correct one. Okay. So let us see in transparent latch, considering T skew and non-overlap condition, what it comes. So in transparent latch, basically I will have two clocks, phi 1 and phi 2 non-overlapping clocks. this as phi 1. Let me consider this as phi 2. Okay, so due to T skew, my clock can change path anywhere between this range. Similarly, this phi 2 also can change path between any of this position. Fine. So basically this distance is T non-overlap, which was meant. Okay, this T non-overlap was our circuit was initially designed for this amount of T non-overlap, and when T skew was not considered. Now if T skew comes into picture, okay, so in worst case I will be considering okay, in the worst case I will be considering which two transitions. First, this transition, that is clock is arriving late, and this transition where clock is arriving early. Correct? Okay, now what would be my D and subsequent Qs look like in transparent latch? Basically, if you remember, there is something called a D3 here, and I have considered D3 has changed much before, has become stable much before any of the transition in the clock has happened. So something like this, D3. Let me do one thing. Okay, so fine. So what would be my Q3 like? It would change somewhere in this region. It would change somewhere in this region. So let this be the point. Okay, and finally my D4 would be, generally there is an combinational circuit after this, so D4 would be after Q3. Something like this. So now let's identify all the delays that are present here. Okay, so first of all, this delay would be T, as we are considering for hold time, so it would be contamination delay. So T contamination clock to Q3, correct? Contamination clock to Q3, and this delay would be the contamination delay, because Q3 to Q4 there is only combination circuit present in between. Okay, now my T hold I have to consider as non-overlapping time has reduced, so my T hold would be from here. Instead of finding from here, it would be from here, because T skew is considered. So it would be, this would be my T hold. So this is my T hold. Therefore for minimum delay constraint, you can see my T skew plus T skew, that is this T skew plus T hold should be less than equals to what all are present. T non-overlap is present, TCCQ3 and TCD is present, right? So it should be less than T skew plus T hold should be less than equals to T contamination delay plus, sorry, let me write it sequentially. So T non-overlap plus TCCQ3 plus TCD, correct? Therefore T hold is less than equals to TCD minus, I'm just writing in the format it has been mentioned in the answer, minus T skew plus TCCQ plus T non-overlap. So this is the correct answer. The correct answer. So let us check the condition. T hold is less than TCD minus T skew. This is the correct answer. Sorry. This is the correct answer. T hold is less than equals to TCD minus T skew plus TCCQ plus T non-overlap. Clear? Any confusion? Okay. If no confusion is there, even you can ask me if any other confusion is there. Just go through it once again. If any other confusions also, if you have, you can ask me, or you can if any confusion regarding today's class, what have been taught today, what has been discussed today, you can also ask from there. So in sequential circuit, the approach is simple. You have to first identify what maximum delay constraint or minimum delay constraint they are asking for. You have to identify whether it has been they are discussing about flip-flops or latches or pulsed latches, and then you have to draw all the propagation and contamination delay terms, and you have to find the corresponding equation. Once you get the equation, solving them is very easy. So this is the procedure you should follow. Okay, any other confusion, anyone? Okay, so all the 10 questions are done. uh, I hope you guys won't find any issues in solving this week's assignments. And still, like, if you need if you find any confusion, go through the lectures, go through this discussion session once again. I hope it would be able to help you clear the problems. Still, if you find any issues regarding previous week's assignments that you guys have already submitted, you can simply give me a mail. I have shared my mail ID multiple times. uh, so it won't there should be no problem in solving them. And if there are no further questions, then we can call it a day. Okay, everyone, thank you for attending. See you.